Hello everyone, it's been a little while since we've been at the board, but here we are. I have a piece of board all cleaned up for us to talk about networking today. And as we approach this festive season, what best to talk about than capacity and throughput in networks? We talk a lot about delay, throughput, etc. And I'd like to just put a little bit of clarity and structure around how we can talk about these different measures of performance in networks. And it will be really good for us to have something in our mind ahead of a little series of conversations that I want to have around the Internet protocol, and particularly our role in the Internet protocol for Web3, how Optimum is really creating the Internet protocol for Web3. So let's talk a little bit about networking and what is a network. So a network effectively, which we generally present as a graph made out of nodes that are connected with what we call edges, which correspond effectively to either physical or generally notional links, so logical links between those nodes. A network can generally be represented as a graph, and it's basically just a collection of these nodes connected with these links or edges. And I'd like to look at effectively two opposite cases of what a network can be. And what we'll see is that effectively this will really help us to think about different types of networks, what we sometimes call topologies, which is really a very fancy word for how these graphs look. So here I have the simplest network. I have two nodes, one node talking to another. And let's think of this as being what we call bidirectional, so they can talk to each other. So suppose that we have a bunch of nodes that want to talk to each other, and in particular, let's assume that we're in the situation with this node, which we're going to call the sender. And for instance, in blockchain, the sender could be the proposer. Okay, so block proposer. And then we're going to have different receivers, sometimes called by Rx. So Rx1, Rx2, and so on, all the way to Rxn. The sender is sending to these receivers, and these receivers, for instance, might be validators, okay, that are basically going to validate what the sender sent. So this topology is what we call generally a star topology, because, if instead of putting all the receivers down here, I just put them all around the sender, then it would look like a star. Again, as I said, perfect for the season. So what happens here? Well, a sender sends to the receivers. In a way, this is like the most natural or, first to come to mind type of topology or graph that you would think in order to have a sender talk to different receivers, to just send it to all of them. So the nice thing here is the sender is only a single hop from each receiver. So you would say, well, maybe delay-wise, that doesn't look too bad. The problem, however, is that all of these different links that I've shown here separately are actually generally all really co-located in a single outgoing link in the input-output of that receiver. So what happens is that this picture, this logical picture, hides an underlying physical reality, which is that, the sender generally doesn't have a dedicated link to each and all of those receivers. It generally has a single link that comes out of the sender, and then these are all actually just logical links, and we'll see later how the Internet protocol suite of solutions actually creates these different logical links. So if we normalize everything to a capacity of 1, really what happens here is that there's an outgoing capacity of only 1 from the sender, And so each of these individual logical links or edges actually has a capacity or total maximum throughput, that's what capacity is, of 1 over n. So it looks like, maybe the propagation speed is pretty good, but actually what happens is that your throughput is not that good. One of the ways that you could do this is you could do what's called time division. So the sender could first send to receiver 1, next to receiver 2, go basically in a round robin way, then come back to receiver 1 when it's done with receiver n. That's one way of splitting the bandwidth. Or you could split the bandwidth by just talking to all of them at once, but sending fewer packets, fewer quanta of information. So this is one extreme. So here, if you look at the throughput that each of these receivers can have, it's basically the capacity, it's basically 1 over n. Okay? Now, if you look at this topology and say, well, do we know anything currently in blockchain that looks like that? Actually, yes, we do. If you consider the Alpenglow system, which is the next version coming up for Solana, it actually has exactly this star topology or exactly this construction for the underlying graph. There's a little bit of a trick here in that some of the traffic here might be what we call lost, which is not necessarily that it was a lost, but it was delayed enough that it looks like it didn't get there. So let's just say it didn't get there on time for it to matter. So there's going to be an extra matter here that we're going to call a 1 over epsilon. So rather than being a full 1, there's some epsilon that we're losing to the losses in the system. Okay? So maybe rather than being 1 over n, it's 1 minus epsilon to the n. And the reason people add coding, and of course some of our earlier sessions at the board have talked a lot about coding, is actually really to deal with this epsilon. This epsilon may not be huge, by the way. It may be just a few percent. So it's going to show up, and you may say at this point, well, the n is pretty large. Like if you think again of, say, Solana, that's like 200, right? So you're like, okay, Muriel, you're dividing by 200, and maybe you're subtracting here like 0.1. Do I really care about the 0.1? That's not the biggest deal. Let's keep that in mind, and let's look at the next example. So here we go. This is basically my star topology. We're going to look at the other extreme of topologies, and that's going to be basically a daisy chain. So what happens in this daisy chain is that I'm going to have my sender, okay, like before, and then I'm going to have all of these receivers, but the receivers are just going to be relaying to each other. So receiver n-1, so receiver 2, and so on, okay? So basically, each of them is just connecting to the next one. All right, we're still going to have this epsilon losses on each of these links. So I'm going to have 1 minus epsilon here, etc. All right, let's look at the throughput of what I can get here in this system. Well, I can get the full 1 minus epsilon going from the sender to this receiver because I'm not splitting up the bandwidth like I did before. This sender only talks to this node, and so it can dedicate all of its bandwidth to talking to that node. It doesn't have to share it with other people. But then this node is also going to talk uniquely to the next node. So all of its bandwidth is being dedicated. So every time I have this 1 minus epsilon. So the total throughput that I should be able to get here is actually 1 minus epsilon. So if I have this sort of daisy chaining, as opposed to having this as a throughput that the sender can get to any one of the receivers, because we have these relays here, the sender can actually get the full 1 minus epsilon. Because remember that when we have in a blockchain a proposer, it's actually sending the same thing. So here it's having to copy things to all of these different receivers. But here it basically sends everything to receiver 1, who's going to send everything to the next node and so on. So my throughput here looks fantastic, 1 minus epsilon. Now, this is the maximum achievable throughput. But remember the coding that we talked about. Here the coding is being done at the sender and then decoded independently at each of the receivers. What about here? Well, you could have the sender code to receiver 1 decode, then send to the next receiver after having recoded it or re-encoded it, receiver 2 decodes, etc. Problem is this is going to take a long time. And as we'll see later, sometimes it's just not possible. Instead, what people do is they use things like, for instance, as you see in Turbine, which is Reed-Solomon codes, or as you see in something like RaptorCast for Monad, is they will use a code which is end-to-end. And in that case, what happens is that a packet has to get through each of these links, okay? So it has to get through the first one, and that happens with probability 1 minus epsilon, that it's successful. Then it has to get through the second one, probably 1 minus epsilon, all the way to, if you look at the very last one, also 1 minus epsilon. So it's 1 minus epsilon times 1 minus epsilon, etc., etc., etc. The throughput is 1 minus epsilon to the n if you do an end-to-end code. So that's really, really far from the optimum throughput. As a matter of fact, even if my epsilon is not very big, say it's 0.1, so it's like 90% probability, if I have an n which is large, say 200, this is going to 0. Okay? It's going to 0 exponentially, actually, with the number of nodes, right? Which is why a lot of systems haven't done this. So if you think of something that's uncoded, like Gossip Sub for Ethereum, it's basically not quite doing this. It's trying to limit how many hops it has, and it's kind of trying to manage, manage the problem. But effectively, this is going to go down exponentially with the number of nodes. Approximation is that it goes basically as 1 minus n epsilon, which means that, if your epsilon is, say, 0.1, with 10 of these, you're basically at 0. Okay? So disaster, complete disaster. Now, what happens when you use RLNC? You encode, and then without decoding, you re-encode. Without decoding, you re-encode, and it turns out that you get this throughput. So the throughput actually is the optimum throughput that you would get if you were, say, sending everything, decoding, then coding again, sending, decoding, which of course would take a long time. So you can see that this topology is actually giving you a much lower throughput from the sender to each receiver. This topology is giving you a much higher throughput. Now here, in terms of number of hops, of course, you have to go through n hops, right? But you know, speed of light is very high. So if even in very simple systems that are, basically public internet, you get something often very close to that. So you may have a little bit more delay, but your throughput is higher. Here you have fewer hops, but your throughput will be lower. And we'll talk a little bit more about meshes and other things next time. But basically, what the Internet Protocol is trying to do is it's trying to manage the throughput and the delay. One of the things to know here is that another way that you could try to operate this, and the way Internet protocols do right now, is that instead of coding, they actually, when something didn't get through, they go back and ask for it. Same issue would happen. You would still get this exponentially decreasing throughput, which means that the scaling basically sticks. Notice that here, I actually don't even care how many nodes I have. Even if I have a really, really large network arranged in this fashion, my throughput is entirely scale-free. So in terms of scaling, here you get a perfect scaling in throughput. And that's basically what we're doing with Optimum. So most networks fall somewhere along these, in the spectrum between these two extremes. For instance, if you look at something like Monad's Raptorcast, or the current version of Solana, which is Turbine, what they'll have is not something that's quite like this. They'll have a few extra nodes. So they'll take basically a version where there's a little bit of this kind of embedded in that. If you look at something like Ethereum, you'll see a system which is like a little closer to the daisy chain, but what we call a mesh. We'll talk about meshes next time. But these are really helpful extremes to bear in mind, the two opposite ends of how you can actually manage a network with a given number of nodes, a sender, and multiple receivers. All right, so with that, we'll pick up here next time and talk a little bit about how the Internet protocol, that protocols that are out there trying to manage this, and how we manage it.